Hello everyone. Welcome to another video on operation research. In this video, we will talk about why formulation is required and how to formulate a business problem into a mathematical equation. So, when we say the formulation is the process of translating real world problem into a mathematical equations, and it is very crucial because the formulation brings the clarity and the structure to complex business problem by defining variables, constraints, and the objective. Once we have the formulation, it would be easy to write the code as well as to build the model and then evaluate the different scenarios that would help in making the data driven decisions. Also, the formulation ensure the consistency in the solution, and it also helps to find if there is any bottleneck in solving the model in the runtime, if there is any runtime issues, etc. So formulation is basically foundation of any operation research projects. That's why we will start with how to formulate a business problem into a mathematical equations. So to take an example, what we will do is we will take the Excel example that we used in our previous video. So the business case that we have is a manufacturer produces four product and it has two different manufacturing unit. The four products are item A, B, C, and D. The two manufacturing locations are MFG1 and MFG2. The data provided to us in this problem was the minimum capacity, which is a conditional constraint, which means the minimum capacity should be applied if and only if the model is selected to produce that item on that manufacturing location. We also have the maximum capacity and then the demand for each of the uh, products. In terms of the objective functions, we have the variable production cost and fixed production cost. So let's get started on the formulation. First, what we will do is we will write the sets for us. So let's say the I is the set of all the products in our model. The next we will again write another set, which is, let's say, the J, which would represent set of all manufacturing locations. Next, let's write the input data. So in terms of the input data, what we have is the minimum capacity, maximum capacity, minimum capacity, maximum capacity, demand, variable production cost, fixed production cost. These are the data that is provided to us. So let's say min C and minimum capacity is at the product and the manufacturing location. So we will say I comma j. This will say this would be minimum capacity for item for product I at jth location. Similarly, I'll just copy this and will write as maximum capacity. Let's say max C. This would also be max of maximum capacity for product I at jth location. We also have the variable production cost and fixed production cost. So let's write let's say the variable production cost, let's name it as something called PV, and this would become variable production cost for product I at location J. Similarly, we have fixed production cost. So let's write that as PF, and this would be fixed production cost for product I at location J. Now we have two sets, we have four parameters, the input data, and now let's define the variables. So what are the decision variable in our case? What we wanted to find out? We wanted to find out how much to produce at each of the production unit for the different products. So the decision variable that will require, the first decision variable that we would need is how much to produce for each product at the two manufacturing location. So let's name this variable as x. This would be I comma j, because we need I is again represent the products, j represent the location. So this would tell production quantity for product I at location j. The second decision variable that we needed, since we also wanted to apply the minimum capacity if a item is produced at a location and the maximum capacity if item is produced at a location. So to find out if a item is produced or not, which are yes or no decisions, what we will do is we'll introduce a binary variable. So let's name this binary variable as y. This would also be at the I comma j level, and this would be 1 if if ith item is produced at jth location. This will be the binary variable, otherwise 0. Correct? Now what we will do is, it's not necessary that you come up with all the decision variable that is required at the starting. It's not necessary that. What you can do is you can keep writing the variables as they comes to your mind, your formulation, and then also keep writing the constraints and the objective terms. And as you keep saying the different, as you keep refining your model, the new business requirement, you keep adding the variables, constraint, and the objective. So what we will do is we will start with these two variables and see if we need another variables later on, then we can also include those variables as well. So let's write the constraint first. The first constraint for us is the minimum capacity constraint. So how to write that? The minimum capacity constraint says the total production quantity for item I at jth location should be greater than the min C, which is the minimum capacity for product I. So the production quantity variable is x I comma j. This should be greater than equals to minimum production capacity, which is the min C. Again, this is at ith comma j location. Now this is a conditional constraint, so we'll multiply this with the y variable, y I comma j, and this would be applicable for I, where I belongs to set I and j belongs to set j, and we can write that via these symbols. The next constraint for us is the maximum capacity constraint. So for now I'll just copy this. This becomes the minimum capacity constraint. I can write here minimum capacity constraint. Then let's write the maximum capacity constraint. The maximum capacity constraint is, the recommended production quantity should be less than equals to maximum capacity. So the recommended production quantity variable is x. The maximum capacity parameter is max C for each product at manufacturing location, and we'll multiply this with the y variable. We will apply this constraint only if it is produced at the item is produced at that manufacturing location, otherwise no. So this becomes the maximum capacity constraint. Now let's also write the demand constraint. So what we said is that the total supply should be greater than or equal to the demand. So what's the total supply now for, so demand is, so as you can see, we did not introduce the demand parameters here. So let's include the demand parameter here first. So what we have is demand, let's write as D, and demand is at the item level. You see, demand is at the product level. So this would be just I. This will tell us demand for product I. Now, the constraint says that total supply should be greater than equals to the demand. So what I'm going to do is first I'll write the right hand term first. The right hand term is that it should be greater than equals to the demand. So this becomes the DI. And I belongs to, for us, I belongs to set I. So this. Now we will write the left hand side of this constraint. The left hand side of the constraint is the total supply. What would be the total supply for item A? The total supply for item A would be how much it is produced at each of the manufacturing location. So if we take the summation of X over J, that would tell us the total production quantity for item or product I. So how we are going to write this? We will take the summation. So let's take the summation sign. Let's say X is at the I comma J, and the summation that we need to take is over J. So J belongs to set J. Now this becomes the total supply, this becomes the total demand. And what we are saying is that the supply should be greater than equals to the demand. Now think of these. Now we have written the variables, we have written the constraint, and this is the demand constraint. Next, what we will do is we will write the objective term. The objective for us is the two things. One is the variable production cost, and the second is the fixed production cost. So to write the variable production cost, we will take sum over I belongs to set I and J belongs to set J. So this is a variable production cost. So X, we will say the X I comma J multiplied with the variable production cost, and the for variable production cost for us is the PVI comma J. So PVI comma J. So how much quantity is produced, multiply with variable production cost, and if you take summation over for all the items at all the manufacturing unit, that would be the total variable production cost. Now let's write the fixed production cost. The fixed production cost for us is, again, the fixed production cost, it would be one time, applicable only once. So what we will say, are we producing that product at that manufacturing location or not? And to represent if we are producing or not, we have taken the variable y, which is a binary variable. So we'll say y I comma j multiplied with, what's the fixed production cost parameter? It's PF. So multiplied with PF I comma j. And the summation would be, again, we will do this, we'll take the sum over all the products produced at all the manufacturing location. Now, the first term is again the variable production cost. The second term is the fixed production cost. Now, this is the first set of the formulation for us. Now, think of this as an, if there could be any infeasibility introduced by these set of the equations, and how to resolve those infeasibilities. So if you look at the equations, and what we are trying to do is we are trying to minimize the set of the equations. So I'll write the min and then close everything in the bracket. So that way we are also making sure that what we are doing, if it is minimization or maximization. Now if you look at the constraint, the first constraint is greater than, the next constraint is less than, and the third constraint is greater than. Now, there could be the cases that the data, the input data that we have are conflicting with each other, and these three sets of the equations might result in the infeasibility. For example, if you have a demand which is higher than the maximum capacity, then the xij cannot be more than the max cij. And here what we are saying is that the summation of x over j should be greater than di. Now, if you cannot produce, if the demand is so high and if you cannot fulfill the entire demand because of the maximum capacity constraint, the model would become infeasible. So how do we resolve these kind of the infeasibility? The first thing that you would ask yourself or the business, which of these constraints are the very hard constraint or the soft constraint? So if you look at, very basic perspective, the capacity of a plant or a manufacturing location cannot be increased overnight. It cannot be a day over day activity. So the maximum capacity or the minimum capacity should be an hard constraint. Now, demand can fluctuate based on the market conditions, other external factor. So this becomes the soft constraint. So to handle the infeasibility that might come because of the conflicting constraint and the data, what we will do is we will introduce a slack variable and make sure that these set of the constraints are feasible in all the data conditions. So since this constraint is constraint is for all the items, and we are trying to remove that feasibility or introduce that, slack variable in this constraint, we need to introduce a slack variable for each of the item. So let's write that decision variable here. And decision variable here with, let's say, slack. This would be for all for the item product level. So this would be, let's call it as missed demand for item or product I. What we will do is we'll come to this constraint and we will say plus, we will introduce the slack I. This way, this will make sure that we have removed the infeasibility that might come because of the data. Now, since we have introduced the slack variable and we are also minimizing the objective term, there will be cases where there might be the cases where to try to minimize the cost, the solver will take the value for these two terms as 0 and it will take all the value for the slack I. So we will introduce an artificial cost in the objective term, and that artificial cost would be high enough and it will only takes the value when it is necessary. So we will take the sum over all the products. So I belongs to I, and let's say we'll take the summation over slack I multiplied with some big cost parameter. I can write as big M. So the big M here represent, and we can write the definition of the big M here. High enough cost higher than all other cost coefficient in our model. So this big M is the cost which is higher than all other cost coefficients. So we can take the max of PV cost, PF cost, and then take the plus one to make this slack cost. And this completes the overall formulation for us. And once we have this formulation, it would be very easy for you to model these set of the equations in any of the programming language, or if you're solving a small problem, then in Excel or any of the other modeling platform. So that's how you formulate an optimization or operation research problem into mathematical equations so that it's easy to solve and find out the issues. Thank you.